Welcome to our latest video on the preparation of amines. This video is suitable for A-level students. By the end of this video lesson, you should be able to understand how primary amines can be prepared from halogenoalkanes and be able to write chemical equations to describe the reactions that take place. You should also be able to explain how nitriles can be converted into primary amines, including the reaction conditions needed for this conversion. And finally, you should be able to explain how aromatic amines such as phenylamine can be made from nitrobenzene. Now, in our previous video, we learnt that amines are nitrogen compounds in which one or more of the hydrogen atoms in ammonia, NH3, is replaced by an alkyl or aryl group. Now, the number of alkyl groups determines whether the compound is classed as either a primary, secondary, or tertiary amine. For example, in a primary amine, there is one alkyl group attached to the nitrogen and then two hydrogens attached to this nitrogen. In a secondary amine, we have two alkyl groups attached to the nitrogen and then a nitrogen bonded to a hydrogen. And in a tertiary amine, all three of the hydrogens in ammonia have been replaced by alkyl groups. Now, the first way to make an amine that we're going to look at today is from halogenoalkanes. Now, amines can be made by heating a halogenoalkane with a concentrated solution of ammonia in ethanol. Now, the reaction is carried out in a sealed tube, and this is because you couldn't heat this mixture under reflux because the ammonia would simply escape up the condenser as a gas. Now, if we look at this equation, we have one bromoethane reacting with ammonia, and the products are ethylamine and hydrogen bromide gas. So CH3CH2Br reacts with NH3 and we get CH3CH2NH2 and HBr. Now, this reaction is a nucleophilic substitution. In a substitution reaction, the reactant atoms swap to form products, and NH3 is a nucleophile because there's a lone pair of electrons on the nitrogen, and a nucleophile is an electron pair donator. Now, this reaction is a little more complicated than it first appears because the amine that's produced is a base. Now, a base is an electron pair donator or a H+, a proton acceptor. So it's very common that the acidic hydrogen halide that is formed in this reaction will react with the amine to form a salt. So, for example, if we have ethylamine and HBr, hydrogen bromide, produced, the HBr would react with the ethylamine to form a salt. This would be called ethyl ammonium bromide. Now, this can be overcome by heating the salt with aqueous sodium hydroxide to liberate the amine. So, for example, if we have ethyl ammonium bromide, CH3CH2NH3 Br-, and it reacts with sodium hydroxide, NaOH, we would form our amine, ethylamine, as well as sodium bromide and water. Now, the formation of the ammonium salt can be avoided if you have excess concentrated ammonia, because this would react with the hydrogen halide formed, for example HBr, preventing the formation of the salt. Now, secondary and tertiary amines can be made in a similar way. Now, the primary amine that forms when you react a halogenoalkane with ammonia also has a lone pair of electrons on it, so it can also act as a nucleophile. This lone pair of electrons on the nitrogen behaves as a nucleophile, and then this will react with any unused halogenoalkane, and the result is successive substitution reactions occurring and the formation of a secondary amine and then a tertiary amine. So the following chemical equation shows what takes place. If we have bromoethane and we react this with ethylamine, we form the secondary amine, diethylamine, and hydrogen bromide. Now, this secondary amine, diethylamine, could react with more bromoethane and form a tertiary amine. And that tertiary amine would be called triethylamine. And once again, the other product would be hydrogen bromide gas. Now, bromoalkanes or iodoalkanes tend to be the most popular in terms of their use for making amines. These are because they're the most reactive halogenoalkanes. Fluoro and chloroalkanes are less reactive, and you remember from studying halogenoalkanes that the main factor that determines nucleophilic substitution reactions is bond strength. And carbon iodine and carbon bromine bonds tend to break a lot easier than carbon fluorine and carbon chlorine bonds. So now let's test your understanding of this with some practice questions. So read through the questions, pause the video, have a go at them, and then we'll go through the answers. So now let's go for the answer to question 1a. So question 1a is asking you to name the primary amine formed when 1-chloropropane is heated with a concentrated ammonia solution, and it's also asking you to draw its full structural formula. So 1-chloropropane, when it reacts with ammonia, forms the amine propylamine, and this is CH3, CH2, CH2, NH2. And as the question is asking you to draw the full structural formula, I've drawn all the bonds here. I've drawn it out in full. So the amine would be called propylamine, and that's a primary amine as there's one alkyl group attached to the nitrogen, and it also has two hydrogens attached. So question 1b is asking you to write a word and chemical equation to describe this reaction of 1-chloropropane and ammonia. So 1-chloropropane and ammonia makes propylamine and hydrogen chloride, and the chemical equation is CH3, CH2, CH2Cl plus NH3, and you get CH3, CH2, CH2, NH2 plus HCl. And there's 1 mark for the chemical equation and 1 mark for the word equation. And if you want to, for the chemical equation, you can actually draw full structural formula for 1-chloropropane and propylamine. So for question 1c, you're asked to explain why amines are usually made from bromoalkanes and iodoalkanes rather than fluoroalkanes and chloroalkanes. Now this is because iodoalkanes and bromoalkanes are more reactive than fluoroalkanes and chloroalkanes, because the factor that determines the reactivity of halogenoalkanes is bond strength, and a carbon iodine and carbon bromine bond breaks a lot easier than a carbon chlorine and carbon fluorine bond. So this is a 1 mark question, so 1 mark if you said that iodoalkanes and bromoalkanes are the most reactive halogenoalkanes, and they're more reactive than fluoro and chloroalkanes. So here's a second question we'd like to have a go at. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So now let's go for the answers to question 2. So 2a is asking you to draw the full structural formula of diethylamine. So full structural formula means you have to draw out all the bonds. So we have CH3 bonded to a CH2, bonded to a nitrogen, which has a hydrogen attached, and then we have another ethyl group, a CH2, CH3 attached to the nitrogen, and there's 1 mark for that. And then for part B, it's asking you to explain why diethylamine is a secondary amine, and diethylamine is classed as a secondary amine because 2 of the hydrogens in ammonia have been replaced by alkyl groups, and in this case, ethyl groups. So you can see there are 2 alkyl groups attached to the nitrogen in this amine, and that's why it's classed as a secondary amine. So there's 1 mark for that. So now have a go at part C, and part C is asking you to explain how diethylamine in this reaction is converted to the tertiary amine triethylamine, which is CH3CH2 in brackets 3 and a nitrogen. Write a chemical equation to help you explain the reaction involved, and this is a 2 mark question. Read through the question, pause the video, have a go at it, and then we'll go for the answer. So now let's go through the answer to 2c. So I've drawn diethylamine here out in full, because I think it's easier if you draw the full structural formula to show what happens. And when diethylamine reacts with bromoethane, you get triethylamine and hydrogen bromide gas. So a C2H5 group takes the place of a hydrogen, and the hydrogen goes with the bromine to make HBr. Now there are 2 marks for this question, so just simply the idea of diethylamine reacting with bromoethane or iodoethane gets you 1 mark. So even if you didn't write a chemical equation, but you just wrote down that diethylamine reacts with bromoethane or iodoethane, that would get you 1 mark. And if you wrote the correct chemical equation, that gets you 2 marks. Now the second way to make an amine is from a nitrile. Now amines can be formed by the reduction of nitriles using the powerful reducing agent lithium aluminium hydride, LiAlH4. And we've come across lithium aluminium hydride previously when we talked about the reduction of aldehydes and ketones. Now, lithium aluminium hydride is a very powerful reducing agent, and you can see from these equations that when lithium aluminium hydride reduces a nitrile, you are effectively adding 4 hydrogen atoms, and you change RCN, which is the general formula of a nitrile, to RCH2NH2. And if we look at this example here, we have CH3CN plus 4 H's from the reducing agent lithium aluminium hydride, and we get CH3CH2NH2, which is ethylamine. Now the lithium aluminium hydride used in this reaction is sometimes called lithium tetrahydroaluminate 3, and this is dissolved in a dry ether such as diethyl ether, which is also sometimes called epoxyethane. Now the milder reducing agent, sodium borohydride, that we also came across when we studied aldehydes and ketones, cannot be used for this reaction. Now remember that a reduction is a gain of hydrogen or a gain of electrons, and the term reduction is also sometimes used to refer to a loss of oxygen. Now lithium aluminium hydride works because it supplies a nucleophilic form of hydrogen, and the carbon, which is a triple bond to the nitrogen, is delta plus because nitrogen is more electronegative than carbon. So that's why lithium aluminium hydride is used, because it does supply a nucleophilic form of hydrogen, and that would attack the delta plus carbon here. Now let's test your understanding of this with some practice questions. So read through the questions, pause the video, have a go at them, and then we'll go through the answers. So now let's go through the answer to question 1. So question 1 is asking you to draw the full structural formula of the amines produced when the following nitriles are reduced. So if you reduce propane nitrile, what's going to happen is you're going to break the triple bond between the carbon and the nitrogen, and you're going to add 4 hydrogens. So I'm going to draw propane nitrile so you can see what happens here when we reduce it. And propane nitrile has 3 carbons and a triple bond between the last carbon and a nitrogen. So what's going to happen here is I'm going to break the triple bond, and I'm going to add 2 hydrogens to the nitrogen and 2 hydrogens to the carbon that's attached to the nitrogen, and then I'm going to end up with the following amine, which is C3H7NH2, and this amine is called propylamine. And the amine is a primary amine because one of the hydrogens in ammonia has been replaced by an alkyl group, in this case a propyl group. And if we have butane nitrile has 4 carbons in the chain and a triple bond between the last carbon and the nitrogen. And if we reduce this, we again break the triple bond and we add 4 hydrogens to the molecule. So what I'm going to do here is I've drawn butane nitrile, and I'm now going to break the triple bond between the carbon and the nitrogen, and I'm going to add 2 hydrogens to the nitrogen, and I'm going to add 2 hydrogens to the carbon next to the nitrogen. So there's my 4 hydrogens, and I'm going to put in the remaining hydrogens, and my final amine is C4H9 NH2, and this is called butyl amine. And once again, this amine is a primary amine. Now it's a primary amine because one of the hydrogens from ammonia has been replaced by an alkyl group, this time a butyl group, C4H9. So here's a second question we'd like to have a go at. So read through the question, pause the video, have a go at it, and then we'll go for the answers. So in question 2, I'm asked to draw the nitriles that form the following amines. So to find the nitriles, I need to cross out 4 hydrogens, because remember, you add 4 hydrogens to a nitrile to make an amine. So I've crossed the 4 hydrogens out here. So I'm going to have a CH3 bonded to a carbon, which has 2 hydrogens attached. And next to this carbon, I'll have another carbon with a CH3 and a hydrogen, and I'm now going to draw a bond to a carbon, and instead of having 2 hydrogens on, it's now got a triple bond to the nitrogen, and that is our nitrile. Now when naming a nitrile, we number the carbons, and carbon 1 is the CN, so this is called 2-methyl butane nitrile. So this nitrile is called 2-methyl butane nitrile because the longest carbon chain containing the CN group is 4 carbons long. That's why it's butane nitrile, and there's a methyl group on the second carbon. So for part B, I once again need to cross out 4 hydrogens, and I'm going to draw a CH3 bonded to a carbon next to a CH3 and a hydrogen, and then there's a bond to another carbon with a hydrogen and a CH3, and then there's a bond here to a carbon, and remember I've lost 4 hydrogens, so there's a triple bond to this nitrogen. This again is a nitrile, and we name the nitrile by numbering the carbons where the CN is carbon 1. So here we have methyl groups on carbons 2 and 3. So this is called 2,3-dimethyl butane nitrile. So it's called 2,3-dimethyl butane nitrile because I've got 4 carbons in the chain that contains the CN, and I've got methyl groups on carbons 2 and 3. Now we're now going to turn our attention to aromatic amines, amines that have a benzene ring in them. And the most common aromatic amine is phenylamine. Now nitrobenzene is the chemical that is used to make phenylamine, a benzene ring with an NH2 group on it. And it's phenylamine that is so important to the chemical industry because it's used in the synthesis of dyes and lots of different medicines. Now, to convert nitrobenzene into phenylamine, we have to remove oxygen and add hydrogen. Now, a reaction where you have a chemical losing oxygen and gaining hydrogen is called a reduction. And to carry out this reaction, we need a reducing agent, a chemical that causes another to be reduced, to lose oxygen and gain hydrogen. And our reducing agent is tin 2 chloride, SnCl2. Now tin 2 chloride, SnCl2, is very unstable. It readily oxidizes to tin 4 chloride. So therefore, we have to make it in situ as part of the chemical reaction. So step 1 makes tin 2 chloride. So you would heat nitrobenzene with tin and concentrated hydrochloric acid. This would produce tin 2 chloride as part of the reaction, SnCl2, and the nitrobenzene would be reduced to phenylamine. However, this reaction is slightly more complicated than it first appears, because when you produce phenylamine, benzene ring with an NH2, this reacts with any leftover acid to produce phenyl ammonium chloride, a benzene ring with an NH3 plus on the ring. And therefore, we have to convert this salt to phenylamine by the addition of aqueous sodium hydroxide. Now, the liquid phenylamine has a high boiling point. It boils at 184 degrees C, and it's only sparingly soluble with water. And this means that a technique called steam distillation can be used to recover it from the solution. Now, steam distillation involves it being distilled at only 100 degrees C, and then it's separated from the water with a separating funnel, because the phenylamine doesn't dissolve that well in water. That's why a separating funnel can be used to separate it from the water. Now, steam distillation avoids the need to distill the pure liquid at the higher temperature of 184 degrees C, and therefore it minimizes possible losses of product that you would get because of this high temperature, because you could get thermal decomposition and the phenylamine could break down into other products. So therefore, this minimizes that. And steam distillation is often used when you have a high boiling liquid and you want to separate it from a mixture, and it works if this high boiling liquid is essentially immiscible with water. Now, when we studied aromatic chemistry, we also studied the conversion of nitrobenzene to phenylamine. And in addition to this, we also learned how to make nitrobenzene from benzene in an electrophilic substitution reaction. So these last few practice questions are a chance to recap that and to test your understanding of not only the work we've studied today as part of the amine topic, but also the work that we studied previously when studying aromatic chemistry. So read through these practice questions, pause the video, have a go at them, and then we'll go for the answers. So this first practice question is asking you to write an equation to show how nitrobenzene can be prepared from benzene. So I've drawn this out here. So benzene plus nitric acid goes to nitrobenzene and water. Now remember, the reaction conditions are concentrated nitric acid, concentrated sulfuric acid, and 50 degrees C. Now it's also okay here to write the equation as I've done so below, with C6H6 plus HNO3 goes to C6H5NO2 plus H2O. Alternatively, you can draw out the benzene rings like I've done on this slide. So question 1A is worth 1 mark if you drew out the equation correctly. And for part B, it's a 5-mark question and you're asked to draw the mechanism for this reaction. So let's go through this mechanism in detail. So the first stage in this mechanism for the nitration of benzene, the nitration of aromatic rings, is the production of the electrophile. So I'm going to first draw nitric acid, and I've drawn it in an unusual way, but you'll see why I've drawn it like this in a minute. So I've drawn nitric acid as HONO2 because nitric acid is HNO3, but I've just drawn it like this so you can see how the electrophile is formed. Now, when it reacts with sulfuric acid, the sulfuric acid acts as a H plus donor, and it's going to give H plus to nitric acid. So the nitric acid is actually acting as a base here. It accepts H plus. Now after we've added H plus to nitric acid, water is lost from this molecule. So the bond between the NO2 and the H2O plus is broken, and both electrons that are being shared here go on to the H2O and water is produced, and also NO2 plus is produced. So in this first stage I have three products. I have H2O, NO2 plus my electrophile, and HSO4 minus. And that's the first stage of this mechanism, because I've generated the electrophile and the catalyst sulfuric acid has been involved in this. Now in stage 2 I have electrophilic attack. So a pair of electrons, a pair of pi electrons, moves from the ring and forms a dative bond to NO2 plus. And the ring of delocalized electrons is broken, so I'm going to draw a benzene ring. I'm going to put a positive charge, because this is my intermediate, now has a positive charge, and I'm going to draw a dashed line which extends over 5 of the carbons. So this represents a broken ring of delocalized electrons. The NO2 and the hydrogen are attached to the carbon in this intermediate. And the hydrogen is now going to be lost from this intermediate, and a pair of electrons is going to move into the ring, so the ring now has its delocalized ring of electrons restored. When this happens, I'm left with my final product here of nitrobenzene, an NO2 on a benzene ring, and a H plus ion. Now, the last stage of this mechanism is the regeneration of a catalyst. And remember, my catalyst is H2SO4. So the H plus that is formed in stage 2 joins with the HSO4 minus that was formed in stage 1, and sulfuric acid is reformed. So my catalyst has been regenerated. And you remember that the products in the chemical equation were nitrobenzene and water. The water is formed in stage 1. The nitrobenzene is formed in stage 2. The remaining products, HSO4 minus and H plus, join together to form the catalyst. So there are 5 marks for this mechanism. So if you drew correctly the steps to show the formation of the NO2 plus, the electrophile, there's 1 mark for that. Now I'd accept someone writing it in words, saying that the electrophile is formed by sulfuric acid giving a H plus to nitric acid and then loss of water. So there's 1 mark for that idea. Now there are 3 marks for the next stage in the mechanism. So a pair of electrons attacking the NO2 plus gets you 1 mark. The correct intermediate gets you a mark. And the correct products from this step gets you a mark. So in other words, nitrobenzene and H plus. And then the last mark is awarded if you correctly showed the regeneration of the catalyst sulfuric acid. So that's the 5 marks for this mechanism. So now have a go at our last practice question, where we're asking you to explain why phenylamine is more reactive than benzene to electrophilic substitution. Read through the question, pause the video, have a go at it, and then we'll go for the answers. So the answer to question 2 is that the lone pair of electrons can get delocalized over the benzene ring, so there's 1 mark for that. So this idea of the electrons on the nitrogen, the lone pair getting pushed into the ring, gets you 1 mark. And then if you said that this would make the ring more electron rich and susceptible to attack from an electron pair acceptor, that would get you the 2nd mark. So there's 2 marks for this question. So that concludes this video lesson. So after watching this video, you should understand how primary amines can be prepared from halogenoalkanes and be able to write chemical equations to describe the reactions that take place. You should also be able to explain how nitriles can be converted into primary amines, including the reaction conditions needed for this conversion. And finally, you should be able to explain how aromatic amines such as phenylamine can be made from nitrobenzene. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @Radachemistry.